In the last decade, the automotive industry has witnessed a major shift in its business strategy, outstretching to reach manufacturing and sales. This shift was actually due to the emergence of new technological trends that played a major role in disrupting this industry and changing the way customers perceive the traditional vehicle. So, as a result of this change, customer preferences diverged away from traditional and conventional automotive needs towards technological features that offered a superior driving experience tailored to conform with their preferences and satisfy their needs. So the trends that actually reshape this industry are numerous and they're diverse, but they boil down to three main pillars, which are connectivity, autonomy, and electrification. So in the ITS field, Intelligent Transportation Systems field, researchers and engineers aim towards building a vehicle that is fully autonomous, that can be connected with other vehicles and to the infrastructure, and that is fully electric. But the thing is that those attributes cannot actually be attained without integrating embedded systems into the vehicles to accommodate for the extensive, demanding computational tasks. So, integrating such systems into vehicles became a must. In the coming slides, I'll be conducting a comparative study between different hardware devices of different classes that have been used in intelligent transportation systems. The devices that we'll be carrying our study on are NVIDIA Jetson TX2 and Xilinx Zynq 7000 automotive grade FPGA. Now, the reason behind choosing those devices is because each of them offer a set of features that is actually crucial and indispensable in the automotive field. So the NVIDIA device is a computer board that has a dedicated GPU tailored for artificial intelligence applications. On the other hand, the Xilinx FPGA is a reconfigurable type of computer that offers utmost flexibility with its reprogrammable logic slices or logic gates. In the coming slides, we'll delve deeper into the organization and architecture of each device to explore how each of them operate under the hood. To simplify the comparison of those devices, we will look at the organization of each from a high-level perspective, where complex components will be represented as black boxes. In this slide, we'll present the ARM Cortex-A9 processor, which is found in the Xilinx FPGA board. It is important to note that ARM stands for Advanced RISC Machines, which means that ARM processors adopt different flavors of RISC architectures in their designs. So the Cortex-A9 is a 32 bits dual-core processor that has a floating point unit attached to each of its cores. Now, the floating point unit is very similar to the ALU, but what's special about it is that it accommodates for floating point operations. So we have the addition, the subtraction, the multiplication, and they all support the IEEE 754 numbering format. So being a 32 bits processor implies having registers of size 32 bits as well. In addition to that, each core has two sets of cache memories attached to it, and each has a specific task. So cache memory is a special type of memory that is much faster than DRAM or the traditional memory type of memory that we know. But the thing is that cache is much more expensive than DRAM, and that's why we encounter it in processors with small sizes. As we can see here, it ranges from 16 kilobytes to 64 kilobytes. So in this processor, we have two types of cache memories, the I cache and the D cache. So the I cache is responsible for storing instructions of the CPU. However, the D cache is responsible for storing data. On the other hand, the NVIDIA Jetson TX2 has the ARM Cortex A57 processor, which is actually very similar to the Cortex A9 in terms of architecture, but however they differ in terms of organization. So both processors might support floating point operations, and they might both have an instruction cache memory and data cache memory. But however, there are some extra components in this organization. So the Cortex A57 is a 64 bits quad-core processor that has registers of size 64 bits, as opposed to the Cortex A9, which is actually a dual-core 32 bits processor having registers of size 32 bits. In addition to that, the Cortex A57 has a level 2 cache memory that has a size that ranges between 512 kilobytes and 2 megabytes. Now, what's special about this type of memory is that it's not integrated in all the cores, but however, it's shared among them. So it is utilized when needed. So all those additions in this organization play a major role in drastically enhancing the overall performance of the device. Shifting to the organization of the Xilinx board itself, we can notice that the green box centered in the middle is the ARM processor of the Xilinx FPGA board. So here we have the two Cortex A9 cores along with their floating point unit engines. In addition to that, we have a level 2 shared cache memory of size 512 kilobytes and a 256 kilobytes on-chip memory. As for the input-output interfacing, we have a CAN interface and the UART interface, and they both permit the communication between the FPGA board and other devices. In addition to that, we have the programmable input-output ports, USB ports, and the gigabit Ethernet port. As for the memory controllers, we have two memory controllers of static and dynamic type. In general, memory controllers are responsible for transferring the data that is found in the memory into the processor and vice versa. So the bulk of the device lies in this huge yellow block, where all the programmable logic devices reside in. What I mean by programmable logic devices are the logic slices that actually comprise of system gates, lookup tables, logic units, and DSPs. And those are the components that can actually be reconfigured and reprogrammed using hardware description languages. Now, the NVIDIA Jetson TX2 board does not share a lot of similarities with the Xilinx FPGA board, but however, they're pretty similar when it comes to I/O interfacing. So they both have a UART interface, a CAN interface, GPIO ports, USB ports, and Ethernet ports. But however, it's important to note that the NVIDIA board has some additional interfaces such as Wi-Fi and Bluetooth, which are actually very important. As for the processor, what's special about the NVIDIA board is that it has two CPU clusters that work simultaneously. So we have the dual-core Denver 2 processor and the quad-core Cortex A57 processor. So in total we have 6 cores functioning simultaneously. In the previous slides, I've mentioned that this board is tailored for artificial intelligence applications and specifically for computer vision applications. And this can dominantly be expressed in the lower part of the organization of this board, where we can see that we have different modules and interfaces that are meant to accelerate and enhance the performance of video and image processing. So we have a video encoder and decoder modules, we have a JPEG encoder module, and a 2D graphics processing interface. In addition to that, we can see that we have a GPU, and we did not actually encounter a GPU in the FPGA board. So what's special about this GPU is that it has 256 CUDA cores. And the main difference between CUDA cores and the normal cores that exist in a processor is that CUDA cores are much smaller in size, they run on lower frequencies, and they're actually designed in a special way to execute matrix operations in the most optimal way possible. And that's why GPUs perform much better than CPUs when it comes to training artificial neural networks. We've discussed in the previous slides that both Cortex-A57 and Cortex-A9 adopt similar RISC architectures in their designs, and this also implies that they have similar instruction set architecture as well. So the ARM has a load store architecture, which means that the processor cannot directly access data that is stored in the memory. In fact, it needs to load this data into its register files, and then the processor executes the desired operation or computation, and then the result is stored back to the memory. So that's why it's called a load store architecture. In addition to that, RISC is known for its lightweight ISA, where most of its instructions are executed in only one cycle. And this actually offers some drastic enhancements in terms of execution time. So we're all familiar with the design principle that says simplicity favors regularity. And this is dominantly expressed in the ARM's ISA, where all of its instructions have a fixed size of 32 bits. So what's special about the ARM's architecture is that it provides a number of extensions to its existing ISA to actually cater for the different computational needs. So we have some digital signal processing extensions and a helium extension, which actually provides a performance uplift for machine learning algorithms. Both devices run different variants of Linux operating system, such as Ubuntu, but however they differ in terms of application interfaces. So the Xilinx FPGA board comes with a bunch of tools and applications that facilitate the process of hardware reconfiguration using high-level synthesis languages and hardware description languages. Some of these applications include Vivado Design Suite and SDSoC development environment. On the other hand, the NVIDIA Jetson TX2 supports a bundle of tools that are tailored for artificial intelligence applications. So the NVIDIA board uses Python as its main language, where it's used to program the board's GPIO ports. In addition to that, it supports the CUDNN tool, which offers drastic performance enhancements when training convolutional neural networks. The NVIDIA Jetson TX2 is widely available on the market and on online retail stores such as Amazon, Newegg, and Best Buy, as opposed to the Xilinx FPGA board, which is only available on the vendor's website. As for the price, the NVIDIA board price ranges between $399 and $479, and this actually depends on the size of memory chosen. So we have the 4 GB version and the 8 GB version. As for the Xilinx FPGA board, its price ranges between $895 and $2,495. And this also depends on the number of logic slices that is included in each device. After conducting a thorough comparative study on both devices, covering different hardware and software aspects, we can conclude that no device is better than the other, because each of them actually offer a set of features that is widely demanded in ITS. So the NVIDIA offers some artificial intelligence enhancements, and the Xilinx offers some flexibility and reconfigurability, and both are actually crucial in ITS. So our judgment must be based on the contextualization of the application that we have in hand. And to better assess the performance of each device, we might in the future use some MCDM methods to actually account for the different weights of each indicator based on the context of application that we'll be carrying our study on.